We have learned how to specify digital systems. Now let's see how we can implement it. The system implementation means the procedure of how to build a digital system from smaller components. And these smaller components, or simple components, or building blocks, can be basic logical gates, can be universal gates, which we are going to define later, or can be some industrial technology library, or we can always use flip-flop to store memory. And also nowadays, when people do reuse-based design, they are talking about using intellectual properties as the building block. Now let's see how we can implement Boolean functions using basic logical gates. By basic logical gates, we're talking about the three gates. The AND gate, which represents the Boolean AND, x and y, which will be true if and only if both x and y are true. The logical OR, x plus y, which will be true if any one of x and y will be true. And the inverter, NOT gate, x prime, which will change a true to a false. And with these three basic logical gates, we can implement all kinds of Boolean expressions. For example, this W based on four variables, x0, x1, x2, x3, it is defined as the sum of four terms. Each term is a logical AND. And from here, we can easily draw the logical implementation of this function. So for example, here we have x0 and x1. So this AND gate implements this term. And then the last AND gate takes x3 and x0. So this one implements the third term. And this OR gate implements the sum of these four terms. And besides the three basic logical gates, there are several other logical gates. So for example, the NAND gate, the NOR gate, exclusive OR gate, and exclusive NOR gate. The functionality of these gates are given in this truth table. And on these first two columns, we list all the four combinations of two input, x and y, start from 0, 0, 0, 1, go to 1, 0, and 1, 1. And then for each of these input combination, we list the output for each of these four functions. So for example, so NAND gate will be 0 if and only if both x and y are 1. And the NOR gate on the other side will be 1 if and only if both x and y are 0s. So with these additional gates, we can sometimes have a much better or more efficient implementation of the system. Consider this example. It has three input, x, y, and z, and then two output, s and c. And this basically implements a full adder, which is going to add up x and y plus a carry z. And the s is the new sum, and the c is the new carry. And the functionality of s is given as the exclusive OR of x, y, and z. And then the functionality of c is given as x, y plus z times the exclusive OR of x and y. So from this definition, we can also draw the logical diagram of this function. So input x, y, z, output sum and carry. And inside we have the basic gates, AND gate, OR gate, and the two exclusive OR gate. So for example, the first one is the exclusive OR of x and y. It will be exclusive ORed with z again to implement s. So this is the input from z. Okay. And one thing is interesting in this example here, it also shows that this exclusive OR of x and y also comes to this AND gate, will be AND with z here, to produce this term. So this is the concept of reuse, which we will discuss later on. Now we talk about this concept called universal gate. It is another way to implement Boolean functions. A gate or a set of gates is called universal if it can implement all digital systems or all the Boolean functions. So this is a very, very strong statement. The gate will be able to implement all the Boolean functions. So how can we verify that? There's no way you can enumerate all the Boolean functions. So how we do this is we start from the definition of Boolean functions. We realize that all the Boolean functions can be expressed as the logical AND, the logical OR inverters. So by putting these three gates together, we have the so-called the standard universal gate. So all the Boolean functions should be able to implement it by these three logical gates. And now the things becomes easier. So for us to prove any logical gate is universal, we only need to show that this gate can be used to implement the standard universal gates, which is logical AND, logical OR, and the inverter. Let's see an example here. We define a logical gate as a Boolean function f of x, y, z. It is defined as x prime y, z plus x, y prime plus y prime, z. And we claim this function or this gate is universal. And how do we prove this? We first want to show that I can use this function block f or this gate to implement the inverter. And how do I do that? I set the second and the third parameter to f as constant 1. So if I plug in this into the definition of f, I got x prime times 1 plus x times 1 complement plus 1 complement times 1. And because 1 complement is equal to 0, so these last two terms disappeared. And then 1 times anything is that thing itself, so this gives us x complement. That is exactly the inverter. And to draw a diagram, I can show this. So this is my logical gate f. And how I feed into this system is I feed x and 1, 1 into f. But however, from outside the box, what people see is I give an input x to the system. And then the system outputs x prime, which is equivalent to the logical NOT gate, the inverters. So next, we show how to implement the OR gate. And similarly, we put the middle parameter to 0, and then plug into the definition of f. So what we get is x prime and y0, so this becomes 0 times z, and z is the new y here. And plus the first variable, which is x, times the complements of the second variable, which is 0 complements, plus the complements of the second variable times the third variable, which is y here. And because we know 0 complement is 1, and 0 cancels this one, so the only thing left is x plus y, which is the logical OR. Okay. And to show this concept, we can draw the same thing here. This dashed box, you feed in x and y, and internally you are taking 0 as the middle parameter. And then this function f gives you x plus y. So from outside, this looks like an OR gate. And similarly, we can implement the AND gate, and which is a little bit more complicated than OR gate or NOT gate. And here is the logical implementation here with two functional blocks. This one, the first one get y complements, the second one get x times y. And from the outside, you see x, y coming in, and then from outside, you see x times y coming out. So this is the logical AND. And because I can implement logical AND, logical OR, and inverters using this f, so I know that f is universal. And I can use f to implement any kind of Boolean functions or any kind of digital systems.